Welcome everybody to another session from Nehru Research. I'm Srikit here, and today in this session we are continuing the partial density of state analysis of nickel oxide for briefing the Hubbard calculations. So in the previous sessions we have covered about what are the advantages of Hubbard and without Hubbard and with Hubbard. So in this final session related to this partial density of state, I would like to brief that how this will dominate or brief the concept. So the periodic or the partial density of state from a standard DFT calculation, which covers the valence band, is dominated by the oxygen 2p states or orbitals with some hybridization with nickel 3d states. So the nickel 3d states are often found to cross the Fermi level, incorrectly predicting the metallic behavior or a very small band gap. And with Hubbard, the partial density of state from a DFT plus Hubbard calculation of NIO will show significant differences. For example, splitting of nickel 3D states. So the Hubbard term will split the nickel 3D band into a lower Hubbard band occupied and an upper Hubbard band unoccupied, separated by an energy gap. So this size of the splitting is related with the value of Hubbard. And the band gap character, obviously the partial density of state will clearly show up. The valence band maximum is primarily composed of oxygen 2p states or orbitals, while the conduction band minimum is derived from the upper Hubbard band of nickel 3d states. So this illustrates the charge transfer insulating nature of Na or nickel oxide. And the hybridization, we can analyze the degree of hybridization between nickel and oxygens, well, the 3d and 2p orbital states by looking the overlap of the partial density of state in different energy regions. So this is actually the representation of that states. So we have taken the basis on S state and P state. You can see both the atoms representation and D states. So you can see that the spin nature, and also it will clearly give an information about the covalent character of nickel oxide bonds and the magnetic ordering for the spin polarized calculation essential for this antiferromagnetic NIO. So that's what we can brief from this picture. So atom-wise representation we can see on this colored region. So for spin polarized calculations, the partial density of state will be spin dependent. We can examine the partial density of state for spin up and spin down electrons on the nickel atoms to understand the origin of the magnetic moments and the antiferromagnetic alignment. So it's about that spin polarization. And the partial density of state of the two nickel atoms in the unit cell with the opposite spin will be shown mirrored to D band occupancies. So as an analysis part, we can open up the results of this interface. 1 minute. Yes. So this is actually the output file, and you can see the band gap information. So from this, we can point out on this that which orbitals will contribute to the density of states as a function of energy. And you can see that the number of valence electron, the valence band index, the spin index, the conduction band index, and the conduction band spin index, along with the valence band conduction band analysis, and also the energy analysis, which shows that how much is the fit error correction used and the final bond energy. And also we can focus on the k-space sampling, the linear scaling. So which brief by comparing the partial density of state obtained with and without Hubbard correction. So it can clearly impact the on-site Coulomb interaction on the electronic structure of nickel oxide and how this DFT plus Hubbard provides a more accurate description. So this is actually the briefing that AMS band documentation for specific steps and keywords required to perform DFT plus U calculations and partial density of state analysis. So thank you.